This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Okay, I think you're ready now. Then we'll go over here. Now, hang on, quiet please. We'll come back to those problems. We want to solve them in the class. We want to get a clear idea so that most of the students can do it in the exam. I find it, although it's very simple, you can't draw in the exam, as you can't draw in the class. You understand it perfectly, but you can't draw it. Understanding and applying the concept you understand is difficult. It's different. So we need to practice that. Okay, why this one is there? So if we go back to a problem, so the problem we're going to solve, if you see your handout, in the second page, you have the exactly same problem. All right? So have a read. That problem over there, it's exactly same problem. This problem you can solve two different ways: gross factor of safety and British standard or Eurocode or Australian standard. It doesn't matter. It will be exactly same principle. But we'll solve it in terms of factor of safety 1 because it would be a very simple problem then. Now, the problem, if you see over here, what it says, you have a tie retaining wall. First thing you have to find out what type is this. Identify the type. So it has a tie over there. The force is T. We don't know the number. What is T at the moment? On the left hand side, you have to retain soil, and that has a distributed load of 10 kPa. On the left hand side, the dredge line is 6.4 plus 2.4, 8.8 meter below, and you have to find the depth of embankment. The problem over here, it's a little bit different. I have typo in the handout, but over here is correct. It says there is a water table in both sides. It could be an example of harbor structure. So you have water one side, water table in the other side, but it also helps you for navigation. Now, if you see the soil properties are given, all the horizontal stress diagram we draw, as I mentioned before, that is in terms of effective stress, right? So what do we try to do over here? We draw the effective vertical stress diagram first. I haven't mentioned over here effective anymore because it's implied. We mentioned it many times. It has to be effective stress, because the earth pressure coefficient Ka and Kp are different than 1 in soil, but it's 1 in water. So we separate them. So we first get the effective vertical stress diagram. You see, above the groundwater table, effective unit weight of water is 17 kilonewton per meter cube. And below the water table, the unit weight of soil is 20 kilonewton per meter cube. So the effective unit weight would be 20 minus 9.8 kilonewton per meter cube, right? Now we could do the same analysis differently. Let's say we could get effective stress differently in terms of total stress, sigma V gamma Z, sigma or UW, if I put UW because we represent water pressure as U, gamma WZ, then effective stress we can write sigma V prime total stress minus water pressure. So what we could write over here, gamma Z minus gamma WZ, we can write gamma minus gamma WZ. This part is gamma prime. So instead of that, I can write gamma prime W. What it means, if I have a soil over here and also water table over here, right? And let's say unit weight gamma is 20 kilonewton per meter cube. Then at 5 meter depth, sigma V 20 times 5 equal to 100 kPa. For pore water pressure, U 9.8 times 5, how much is this? 49? Can you multiply that, anyone? (49 kPa). So I can write this total sigma V prime equal to sigma V minus U 100 minus 49, it would be 51 kPa, right? That calculation I can actually do it separately. Over here, sigma V prime equal to 20 minus 9.8 times 5. It should give you exactly same number because we already derived that. It is exactly the same thing. Now, in terms of pressure diagram, what does it mean? That you also need to know. So, let's say if I draw the pressure diagram in terms of total stress. So, total stress, this one go to up to 100. Let's say we do not need these anymore. We drive whatever we need. As I said, that would be the slope. That is 20 over there. For pore water pressure, write sigma V. Sigma W would be, this is 9.8. So we find it how much? 49. So total stress minus water pressure, if I put minus, that will give me the effective stress diagram. So what happened? This part, if I take it over there, this part would be, let's say that part. We need to take that part out. The pressure diagram would be a little bit less over here. So it will come to 51. That is sigma V prime. It's equal to. Very simple thing, but in terms of understanding could be different. So what does it mean in terms of effective stress if we do as a whole like that? As a whole, how we can do that? Simply, instead of gamma, if we use gamma prime, right, then you would get effective stress. But when you draw a diagram after water table, the initial diagram, the slope was 20, the slope was 9.8, so it will be 10.2. You will see the slope of the diagram will change below the pore water pressure. Yep.
Can that slope be in the middle in between those two, steeper?
The slope is, you can say in between. I can say the number. The slope would be 20 minus 9.8, so it would be 10.2. As I said, the equation, it's actually an equation of a straight line, y equal to gamma z. So you can write y equal to mx. The m is the slope, and that is basically this one. If we have intercept like over here for net pressure, that is nothing but what is Q naught you have over there. So it would be C. Something like that. Now, if we want to draw pressure diagram, keep in mind, if we have something above the water table, it will come through a slope. But once it hit the water pressure line, from this diagram we can see the slope should change of that line. That is very important. That is, should be there. So over here, I think I'm taking too much time, so I should go a little bit faster. So what I did, it's a qualitative diagram. So first 10 kPa, see that 10 kPa is over there. That is a rectangular surcharge load for vertical stress diagram. Then the stress up to 6.4 meter, it increased at 17 kilonewton per meter cube, so it comes over here, right. Once it hit the pore water pressure, although the pore water pressure in both sides is same level, they cancel out, but the diagram over here, because of this reason, from 20 or 17, we take 9.8 out, that would be the slope. It would be different slope. So what I tried to do over here, I draw a mild slope. It was increasing at 17 rate. Now it's hopefully increasing 10.2, or not 10.2, 17 minus 9.8 rate. So it would be 7.2 rate. Got the idea? We can use gamma prime to calculate those directly to effective stress. If you remember in soil mechanics what I told you, you draw the vertical stress diagram, you draw the pore water pressure diagram, take off pore water pressure from vertical stress, you get that. We can do it. Now we are more confident with the calculation. If we use this concept over here, it's nothing but if you change that 1 to gamma prime, instead of gamma, just change to gamma prime, it will do the effective stress analysis. Okay. Now 17 times 6.4 should give you 108.8 kPa. That would be a surcharge. It should come over here 10 plus 108.8. This one now increase in terms of gamma prime. The total height of that from that to that 2.4 plus d, 2.4 plus d times gamma prime. So the total effective stress, the total effective stress would be 10 plus 10.8.8, now 108.8 plus 2.4 plus d whole times d gamma prime. Yeah.
So this time we don't keep adding it as we go. Like you know how last semester we kept adding, so the 10 plus the 108.8 and then keep adding as you go.
Oh yeah, it's the same, exactly same. But I write it separately because I can't accommodate all of them over there. So what I did, 10 put over there. That triangle, the base is 108.8, so that I can use that on in the calculation later on. And that triangle I separate, so that I can use that one in later calculation. On the, okay, before going that, if you check first we identify that is anchored to retaining wall. Then what are the changing point on the left hand side? The changing point is the starting point that is start with 10. Then we might have a changing point for T, but it's not in the soil, so we ignore that. We come up to the water level, that is the changing point. Then on the left side there is nothing changed, so it goes directly to the bottom. If you now get into the left hand side, you have pore water pressure. We didn't consider because we directly go to this equation, sigma prime equal to gamma prime times z. So we get this one from here directly. The vertical stress on left hand side would be d times gamma prime. You could do the same way. You could do the pore water pressure total stress diagram and then take up pore water pressure. It would be exactly same, d times gamma prime. Got it? It would be exactly same on there. Okay. Now once you get the vertical stress diagram, I always go through vertical stress diagram because it gives you the sense whether you are doing it right. How? The vertical stress as you go deeper, it always increases, and you have a tentative idea of the magnitude, because on the left hand side of the retaining wall, height of the soil is higher. This diagram would be bigger, the number, than the left hand side. Now with that, now go back to the assumption of cantilever retaining wall. First, on the left hand side, everything is passive. So we multiply that tiny stress over there, d times gamma prime with k, that would be 3.85 over here. This magnitude increase, right? This side it should increase a little bit lower, but I could not put the numbers over there, so I keep the size remain same. So that size and that size same, but it should go down because Ka is smaller. Now once we went there, we can see we can divide the forces according to their simple shape. The first one is a whole rectangle, right? And the whole rectangle is 1. What is the magnitude of that? 10 times Ka. Ka was 2.6, so it would be 0.26, so it would be 2.6 over here, the magnitude. This one over here, 108.8 times Ka, that is 0.26, it comes around 28.28. So that from there to at the bottom of the diagram it remains same. The bottom triangle, number 4, we multiplied that one with Ka. Again, it was gamma prime was 10.2 times 0.26. It becomes 2.65 times 2.4 plus d. So we get the diagram now. So how many components we get over here? The first component in active side, 1, 2, 3, this rectangle 3 and 4. We subdivide them because we know where is the centroid of these shapes, so that we can take moment. Left hand side is remains same, only one component, so it's pp. Now we are ready to take moment. Then where should we take the moment? Where moment 0 in this case? Yes, total moment is 0. Don't see that one. Where is the moment 0 now? Yes, where the thigh connected with the retaining wall. So if we go back to original assumption, we say the point of rotation would be the connection of thigh and retaining wall. So we know all the forces, right? So we have to take moment from the point of rotation. So point of rotation is actually over there. Now forces is nothing but the area of the force diagram, right? So P1, for example, P1, that tiny one, so the diagram would be 2.6 is the magnitude over here times the height. What is the height? Height would be 6.4 plus 2.4, 8.4 plus d, that is the height. So the diagram of 1, PA1, 2.6 times 8.8 plus d. Now tell me, where is the moment distance? How do you find the moment distance? The rectangle, it is a sorry, yep, keep going. Yeah, middle of the rectangle, correct. But what is the point of rotation? At t. And t is 1.5 meter from the top. So the middle of the rectangle would be half of 8.8 plus d. But you are not taking moment from the top, you are taking moment from t. And t is 1.5 meter below from the top. So you need to take out. So the distance from t to the center of this rectangle is 8.8 plus d by 2 minus 1.5. Got it? For every forces you have to do the same thing. If I do all these things, do you want me to explain it? Because I still want to practice the exam questions. Okay, I will go quickly. If it takes one more class, no matter. Okay. Now P2, what is the P2? P2 is this triangle, right? What is the area of this triangle? The height of the triangle is 6.4, base is 28.2, so half times 28.2 times 6.4, 90.5, that is the force. The location of the force, it should be from top 2/3 of 6.4. So from top 2/3 of 6.4 minus that distance 1.5. So that is the moment distance. So if you multiply that, you will find M2. P3, that one is that rectangle over here. So the height of the rectangle 2.4 plus d times the width 28.8, that is the force. The moment distance would be the half of this height plus 6.4 minus 1.5. So half of the height 2.4 plus d by 2 plus 6.4, so you get top, minus 1.5, you come to t. Got it? Following it? Very good. The only remaining thing is this one, P4. P4 is the magnitude over here, you can see 2.65 times 2.4 plus d times height. Height is exactly same, 2.4 plus d. So what I write, 2.65 times 2.4 plus d whole square, because two of them over there. The moment distance of this one would be 2/3 of the triangle height. So 2/3 of 2.4 plus d plus 6.4 minus 1.5 to come back to tie point. So that is the moment we got. We got the moment force and the moment distance. If we times them, then we'll get the moment. Now we also have tie force, and the distance of tie force and the point of moment is equal to 0. So that would be 0. Now if we see back over there, the moment for 1, 2, 3, 4 are anti-clockwise, and moment for passive P5 and T is clockwise. So if we equate them, let's say factor of safety equal to 1. If we equate them, then it becomes a cubic equation. If this is in the exam, right, then you can use any calculator that can solve this kind of problem, and let's give you a number, d equal to 3.16 meter, right? So if you have this problem in the exam, don't be panic, answer all of them, all the other questions, come back and slowly solve it. It would be too complicated. I will make it simple if this is there. Okay, but the concept, you have to follow the concept, that's very important. Now once we know the d, let's say d is known, right, then we can draw the pressure diagram again with exact number. then if we take the summation of horizontal force equal to 0, then we will find T. If we go back to exam question in 2013 or 14, we will see I gave you a D, a non-D 3.16 for example, and I ask you to calculate T. So problem become very simple, but you still have to draw the pressure diagram, otherwise you can't do it. So a complex problem can be very simple in the exam. So you don't think like it looks very complicated, you don't have to practice for the exam. You still need to practice to understand the concept, practice it like like you don't have to think in the exam. If you think, you'll probably try to make lots of mistakes. And if you think, try to develop your own theory, you probably come up with many different theories that I can see in the exam paper sometimes. So what do we do over there? If we put the D equal to some number 3.16, then the tie I get 121 kilonewton. Now there is a catch in the problem. The problem over here, it says, go back, the ties are 2 meters apart. So all the calculation in the retaining wall we do, we assume the thickness of the retaining wall is 1 meter, the previous concept. If we know the design for 1 meter, you can extend it to 100 meter, 200 meter, 300 meter, it doesn't matter. So all the calculation over there is in terms of 1 meter, but the ties are 2 meters apart. So that means that force would be double in one tie. So that's why I multiply 2 times T, and that is the force. The tie force, I should write it over here, T by 2, it will come that number, but for simplicity I put T and then multiply with 2. So that is the solution. Okay. We still need some time to explain some of the concept. Of course, as I start this lecture with saying that everything we do over here is in terms of Rankine earth pressure theory. Rankine earth pressure consider possible failure state, failure stress of soil. So the pressure diagram we draw, it not necessarily develop in the soil. It could be different. But if Rankine pressure is theory, before failing the soil, that pressure would develop. So that satisfies the design criteria. If we design based on Rankine theory, it will be safe. But something happened apart from those Rankine theory. So it calls soil arching. So flexible sheet pile wall lead to lateral pressure redistribution that do not correspond to Rankine active or passive pressure. So yielding of wall lead to constrained soil movement at or near a building. Let me explain it a little bit. So constrained movement means soil doesn't flow like water. It flows, but it would be restricted. That because the soil particle has intergranular friction, shear force, so that doesn't flow. As a result, stress near the wall redistributed as the soil establish equilibrium. So there would be a pressure distribution that wouldn't be exactly same as Rankine theory. This phenomena is analogous to structural arching, therefore it calls soil arching. So let me explain in a very simplistic way what happened. So if we have a retaining wall and somehow that structure, let's say it remains same, and somehow it bulges over there. That means it's moved toward over there. So originally soil was over there. If it happened, then some soil from here will move this direction. So they will come over here. But what happened, at some point it will form kind of an arch. All of this soil will slowly move this side, but over here it will form an arch. It will hold the soil in our other side. So what happened, whatever the pressure is supposed to be there, it would not be there. The stress will decrease in that point. So if we have seen, do you know arching, structural arch? If you go to very old buildings, then you will see in the opening of window or door, they have kind of arch. So what does it mean? You do not need to put any reinforcement of this kind of structure. If you put some block, it's not like that. Because of their shape, you see, this thing cannot go in. It cannot fail. It will hold itself. So it gives lots of lateral pressure, but it is stable in vertical direction. So this kind of structure, you do not need any reinforcement if you can do. So in soil over here, it will form kind of arching. But it depends on many things. Not necessarily it will form like that. It could be any shape. So I put two examples over here, one from Craig soil mechanics, figure 6.24, and another from Muni Biddu, figure 15.22. One for very dense soil, other one is medium dense, and two different failure. So it depends on how the flexible wall deflect. So what happened, this one for example, it has active side and passive side. Just think about if we are considering above the point of rotation. So the pressure redistribution in dense case, this was the original shape, but the active pressure increased over here significantly. And passive side, it could decrease over there. The second one is more like resembling this case. So what happened, the pressure diagram was this. It flexed over there. So the pressure increased beyond the Rankine theory, then decrease, then beyond the Rankine theory again. It's kind of arching over here. In two sides of the arch, you get higher pressure. Again, on passive side, this thing goes up. It's always the same case. In passive case, you will see the maximum passive stress in Rankine theory occurs at the bottom. But over here, it goes somewhere near to the surface. Whether it goes beyond the original line like that, it depends on how it's deflected. But the main point is that the soil distribution, what you think, in Rankine theory may not necessarily be same. A few facts we need to remember. It depends on flexibility of the wall, how flexible of that wall. So when you design, choose a section. For example, you find maximum moment, and then you find section modulus, and based on the section modulus, you find an appropriate section for this retaining wall. Choose the appropriate one that doesn't behave as flexible. This behavior could be significant for cohesionless soil. It makes sense. For sandy soil, it would be significant. It also increases with soil density. As I said, there's two diagrams, it's two different density. It would be different for density. In normally consolidated soil, we do not need to worry about that, but if it is over consolidated soil, it would be a problem. When I say normally consolidated and over consolidated, they are not really sand anymore, they could be silty soil. So if they are normally consolidated, they didn't experience any stress higher than current stress, so it will be normally consolidated. If they experience higher stress in previous case and in the history, then it will be over consolidated. We also need to remember, the thing is that the Rankine pressure theory, whatever we come up, it could be different for arching. So there is a difference between theory and what we do, but we can minimize those. The other case, higher active pressure, we get the active pressure over there, it's much higher. As I explained the failure case in the second case, passive failure for the anchor retaining wall, it is possible in this case. The passive thrust closer to the ground surface, it goes to the ground surface, the maximum passive thrust. Just think about it. If you're taking moment over there, the location of force goes up, the resistance moment is lower in this case. If it is a stiff wall, but K0 is higher than 1, that means over-consolidated soil, so it could give us higher moment and tie force. So this is so far how we design the anchor retaining wall. There is a little bit few here and there, few things. If we practice these, it will cover most of it. But before going to practice, let's talk about like Australian standard consideration. The method we are learning, gross method of safety, if you learn the principle, you can apply these standard quite easily. What it does, it tells you, it guides you to consider some special consideration. For example, Australian standard for retaining wall tells you whether there is any live load or distributed load on the retaining wall over there, is there or not. You have to consider a minimum live load of 5 kPa. If it is there, it's always welcome. You consider that one in the calculation. If not, then that 5 kPa is always there. It's important because it comes in the pressure diagram and the calculation. It should be there then. The water table in the retaining wall, if the retaining wall like gravity wall or cantilever type gravity retaining wall we learned in last semester, if they are in bridge apartment in roads, that may be okay. But over here, because we make sure those are drained, but if we are considering harbor structure with sheet pile, then we must consider the water table and the worst possible case. It not only varies season to season, because it's rainy season it will be higher, but it also varies year by year. It's not necessarily this year you get the higher water table. You should consider several years to find out the worst possible water table. Now, when we calculate the loads, like unit weight and everything, we need to factor them. For total unit weight, we have to factor by 1.5. We need to increase it. If there is any dead load, we need to increase by 1.25. If there is any live load, we have to increase that 1.5 times. Unit weight of water we naturally do not change. It's pretty unique, so it will be 1. Now, we also need to apply some factor for different strength parameter for different cases. So, soil uncertainty factors, these could be because of the strength and serviceability, and they also depends on the soil types. For example, if it is in the road, right, in the approaching road in the bridge, we can fill behind the retaining wall and we can control the material. We could choose highest quality of the material. So if we have fill and control, see that reduction factor is very close to 1. But if it is uncontrolled fill, the reduction factor for phi and c, they are quite small. If it is in situ condition, we don't know, it would be around this range, right? For serviceability, again the same way. These are the control situation, uncontrolled situation, that means worst possible probably condition, and this would be in situ condition. That are the factor we need to consider. So when we calculate different factors like C5 that eventually turns to Ka and Kp, it would be affected by those factors. When you calculate the load and loading diagram, that would be factored by the load diagram over there, and then you do the same analysis. Okay, we still have some time to go back to this problem now. Try this one first. Now you have pore water pressure, and I explain how pore water pressure changes. First, identify, is it cantilever or anchor? Yeah. See, you don't have to calculate it. You just need to apply your concept, draw a freehand diagram. It is right, right. You got full marks. Just I want to see whether you can draw it. Just draw freehand. You don't have to think. You do not have to write. Just draw.
When you do thread a hole for the pressure diagram, when you times it by the 0.2 whatever, you make it like smaller, is that right? But the slope stays the same because it's still the same either way.
Which one can I do?
Just say for the top part above the water here, right? So it'll be active. So say you draw it like that, right?
Yeah, yeah, you
And
can.
then if you multiply it by 0.26 or whatever, because it's active, do you have to draw that smaller, like together? Because it'd be
No, no, no. It would be even higher. It says multiply that factor with the unit weight of soil.
yeah. So if we go up for this point, so the contrast diagram, we go gamma z, we get pressure here. Now we multiply that by 0.26. Will it stay the exact same, or do you have to draw it smaller? You know what I mean?
Oh, no, it doesn't matter. You just put like qualitatively, relatively different shape. That's fine. What I'm saying, you have active and passive side, right?
Yeah.
So if you know the passive would be bigger, just make it bigger a little bit.
Yeah, bigger than the active.
Yeah.
But when you translate it from the vertical stress diagram to the horizontal stress diagram,
Or you should be,
the exact
in
same.
K, should be smaller.
Okay. But then that changes the slope, even though the unit weight's the same. You know what I mean?
Yeah. That change the slope.
But the unit weight stays the same,
Yeah, it's not related to unit weight, right?
isn't it? I thought.
It Ka times unit weight. That would be the slope.
Okay.
If there is no C.
Okay. So for the horizontal stress diagram, the slope is just the unit weight. I mean for the
Yeah,
for the
vertical stress is the unit weight.
But
Yeah.
for the horizontal stress, it's the
K,
parameter times.
yeah, parameter times.
I can control the uncontrolled field.
Oh, when you fail it,
Yes.
sometimes you roll it, make it very strong. That is control, good material. And sometimes you just fail it without controlling it.
Oh, without control. Like that. Okay.
Yeah. Anyone? Can you show me? Can you show me the diagram? Do you find it very difficult? You're not drawing it, so I assume like you find it difficult. Well done. Only thing is missing. Where is point of rotation? Then draw the passive. Where is point of rotation? First, identify whether it's cantilever or anchored retaining wall, sheet pile wall. Yeah, you're right. You're right.
Kind of.
Yeah,
So you take the water from that and then you translate that to that.
yeah. Water should be up to this from this level. That's wrong. See, you're not drawing it. You find it difficult or something?
We're just discussing it.
Yeah, you're not drawing it. It means like you probably find it difficult.
Yeah.
We're doing that one there, the 2012. So
Yeah.
you've got your point of change.
Yeah, you're right with that.
And then, so
Draw
I've
the
got,
line.
okay, so
Wow.
if I'm drawing the passive side first,
Yeah, what are the changing point?
the
Surface,
changing point is
surface,
the surface,
0.
and then
Then water table,
the water table. Okay. So
Nothing
it's
else.
going to have,
start from 0. Yeah, go to water table, then the slope decrease. Yeah, that's correct. What is the point of rotation?
Pointer? Yeah.
Yeah, it's not. What is distributed load? Vertical stress. Yeah, you're doing it right. Keep going. You're right. you mix the point of rotation. You are right. Yeah, that's correct. You'll get full mark. I find the first student who get full mark. What is point of rotation? Oh no, draw the horizontal stress diagram. Yep.
I have a question here, so is it okay? Or?
You mix the water table in left hand side.
This one here?
Yeah, the slope will change in the vertical stress diagram.
This one you were given the effective unit weight.
Mm-hmm. Oh, I said this one is wrong.
Oh, did you?
I corrected over there. Did you?
But if it was like, let's say, does the slope change? If this was effective, given, does this slope changes here or?
No, then it don't change. It will follow that 20. Okay, I'd probably let it go, but I find only one student got it correct over there. Vertical. Yeah, very good.
Water here, P
Yeah,
totally
yeah, you're right.
P.
Very good.
Okay.
I'll come back to you. You missed the point of rotation.
Is that almost right or close?
No.
Not quite?
Why this one?
No, I
increase?
figured that was wrong.
Get the vertical.
Not quite right either. Now, I just have to point out, I did soil mechanics last year,
Yeah, yeah.
not last semester.
I think this side is okay, but that side should be lined up.
It should line up, yeah, no,
Yeah,
I know.
it should line up.
It's just hard, yeah.
And the point of rotation is missing. Then it would be the active and passive would be reversed. Okay, that's the end of this class. But practice this one. If you have problem, I probably won't post the solution for this one. I want you to try yourself, because anyway, if I give you the solution, it doesn't help you. Because every year, if I just little bit change water table, tie, and here and there, it's completely different problem again. So you have to learn it how to solve. Okay, thank you.